Wishing Upon a Cstr is an episode of the Degrees of Freedom Project videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. The study of chemical kinetics reactor models almost always begins with the three ideal homogeneous reactors. Even though most commercial chemical processes are heterogeneous, meaning that two or more phases come in contact with the reaction happening at the interface between the phases. The rationale is that homogeneous models are much simpler, and understanding them well makes it easier to understand the heterogeneous reactions when they are introduced. No reactor truly achieves the characteristics of the three ideal reactors, so they should be considered limiting cases, although some reactors come close. The first ideal homogeneous reactor is the batch reactor. The reactor is fed with reactants. It is then sealed and the contents reacted. It is then opened and the contents removed. During the reaction, the reactor is assumed to be well stirred so that there are no concentration gradients across the reactor. So at any instant in time, the concentrations are uniform, but the concentrations evolve with time during the reaction. The second is the continuous stirred tank reactor, or Cstr, also known as the well-mixed reactor. It is a steady-state reactor. The entering feed is considered to be instantly mixed uniformly throughout the reactor, so there is a step change from the inlet conditions to the tank and outlet conditions. The tank and outlet flow have the same concentrations. Because it is at steady state, the conditions do not change with time. Students often puzzle over how a Cstr works because nothing seems to be changing, but things are reacting. However, if you follow the math, it all works out. The third is the plug flow reactor, or PFR. It is assumed that the entering feed flows down the reactor tube as a plug, so the radial concentration is assumed to be uniform, but the axial concentration evolves down the length of the reactor, or perfect mixing in the R direction and no mixing in the Z direction. Once it has reached steady state, the concentration at any fixed point in the reactor doesn't change with time. It is important to realize that the Cstr and the PFR do not start up in their steady state conditions. It takes time to get there. Plant managers will tell you that startup and shutdown are the most stress-inducing parts of any plant operation. The transient stages can be modeled, but doing so is beyond the scope of what we intend to do here. It is common practice when studying chemical reactor engineering to rewrite your chemical equation so that the stoichiometric coefficient of your most important reactant, species A, is -1. We basically divide through by the absolute value of the stoichiometric coefficient. With that change, the reaction rate with respect to A becomes the negative of the reaction rate. The expression negative R sub A should be understood to be the same as R. In this video and the next one, we will limit ourselves to the case of irreversible kinetics with power law form, as shown. We write down and simplify the reactor overall balance equation as derived in how did you think I would react? For the batch reactor, during the reaction, there is no input feed or output stream, so n.j0 and n.j are both 0. Since the concentration is uniform at any instant in time, the reaction rate is the same throughout the reactor, so Rj can be pulled out of the integral, and the integral of dV over Vr is just Vr, the reactor volume. Since Vr is constant, it can be pulled into the derivative, and dnj over Vr become dCj, so dCj dt equals Rj. As usual, we will focus on species A. The moles of A in the reactor is the initial moles of A times 1 minus the fractional conversion. If you don't believe it, start with the definition for fractional conversion and solve for Na. Substituting in Na0, 1 minus Fa, for Na gives us ultimately negative Ca0 dFa dt. We will use this expression to model the reactor in terms of the fractional conversion. We also want to model the reactor in terms of the concentration of A, so pulling Vr inside the derivative gives us, as before, dCa dt. We will here solve for the reaction time in two parallel ways, in terms of Fa and in terms of Ca. Starting first in terms of Fa, separating the differential equation gives us the integral of dt from 0 to t. Don't freak out your math nerds who want a dummy integration variable. Equals Ca0 times the integral from 0 to Fa of dFa over negative Ra. So the time to reach a given fractional conversion is Ca0 times the integral from 0 to Fa of dFa over negative Ra. We will have to express Ra as a function of Fa to do the integral. On the parallel path with the concentration, we separate the equation dCa dt equals Ra, and then integrate dt from 0 to t, and dCA over Ra from Ca naught to Ca. The result is that the time to reach a given concentration of Ca is given by the integral of dCA over Ra, where Ra is a function of concentration. You'll often see the final integration written with a negative sign in front of the integral and in front of the reaction rate. Here, we have graphical interpretations of the last two expressions. In terms of Fa, if we graph Ca naught over negative Ra as a function of Fa, then the area under the curve from 0 to Fa is the time required to run the reactor. In terms of Ca, if we graph 1 over negative Ra as a function of Ca and take the area under the curve from Ca to Ca naught, it is equal to the processing time for the reactor. The Cstr is steady state and spatially uniform. Starting with the reactor general balance equation, the accumulation term is 0 because it is steady state. Because it is spatially uniform, that's what well mixed means, R sub j can be pulled out of the integral, and the integral of dF over the reactor volume is Vr, giving n dot j naught equals n dot j plus negative R sub j Vr. Again, following our favorite reactant, species A, the reactor volume is the inlet minus the outlet molar flow rate of A divided by negative Ra. You should check to make sure the signs make sense to you. We will now define the space-time, tau, as the reactor volume divided by the inlet volumetric flow rate. For constant density reactions, the inlet volumetric flow rate and the outlet volumetric flow rate are the same. For non-constant density systems, they are different. Again, we are considering only constant density systems. The units of tau are volume divided by the volumetric flow rate, which works out to time. It is the time required to fill the reactor at the inlet flow rate. For the constant density case, it's the same as the mean residence time, or the average time that a particle of fluid spends in the reactor. We again do the parallel development in terms of Fa and Ca. For Fa, the exiting molar flow rate of A is equal to the entering flow rate times 1 minus Fa. Plugging that expression back into the previous equation for n dot A, we get that minus Ra times Vr equals n dot naught A times Fa. Plugging v dot naught times Ca naught in for n dot A naught, we get that tau, which is still Vr over v dot naught, is equal to Ca naught times Fa over minus Ra, where Ra is a function of Fa. For Ca, since it's a constant density system, the inlet and outlet volumetric flow rates are the same. Plugging in v dot naught Ca naught for n dot A naught and v dot naught Ca for n dot A, we get that tau, which is still Vr over v dot naught, is equal to Ca naught minus Ca over negative Ra. Again, you should check to see if the signs make sense. Here, we have graphical interpretations of the last two expressions. In terms of Fa, if we graph Ca naught over negative Ra as a function of Fa, then the area of the rectangle from 0 to Fa, with the height of Ca naught over the value of negative Ra at Fa, is the space-time required to run the reactor. So given the reactor volume, you can calculate the volumetric flow rate, or vice versa. In terms of Ca, if we graph 1 over negative Ra as a function of Ca, and take the area of the rectangle from Ca to Ca naught with a height of 1 over negative Ra at Ca, it is equal to the space-time of the reactor. Again, given the reactor volume, you can calculate the volumetric flow rate or vice versa. For the PFR, or tubular reactor, totally tubular man, we will apply the reactor mole balance equation to a differential element in the reactor. The differential element has the volume of dV. Into the element, the molar flow rate is n dot sub j, and out of the element, the flow rate is the input flow rate, n dot sub j, plus the differential change, dn dot sub j. We assume that the concentration in the differential element is constant. In other words, it is like a mini Cstr, and that the reactor is at steady state, so the accumulation term is 0. The result is that dn dot sub j dV equals Rj. Substituting in species A for j, and separating and rearranging the equation, we get that the integral of dV from 0 to Vr is equal to the integral from the inlet molar flow rate to the outlet molar flow rate of dn dot A over Ra, or Vr equals the integral from n dot A naught to n dot A of dn dot A over Ra. Again, we'll derive the results in terms of Fa and Ca, but this time they don't quite fit in parallel. For Fa, as before, n dot A equals n dot A naught times 1 minus Fa. Taking the differential, dn naught A equals negative n dot a naught dFA. Substituting into the integral and dividing through by n dot a naught, we ultimately get that tau is Ca naught times the integral from 0 to Fa of dFA over negative Ra, with Ra as a function of Fa. If you recognize this equation, it's the same as the one for the batch reactor, with T replaced by tau. Don't forget that T is the processing time, and tau is the space-time, or reactor volume, over the initial volumetric flow rate. In terms of Ca, tau is the integral from Ca naught to Ca of dCA over Ra. Again, the same equation as for the batch reactor, but with the processing time replaced by the space-time. Remember that you can't measure tau with a stopwatch. You need a reactor volume and a volumetric flow rate. Here, we have two graphical interpretations of the last two expressions. In terms of Fa, if we graph Ca naught over negative Ra as a function of Fa, then the area under the curve from 0 to Fa is the space-time required to run the reactor. In terms of Ca, if we graph 1 over negative Ra as a function of Ca and take the area under the curve from Ca to Ca naught, it is equal to the space-time for the reactor. Yes, the graphs are the same as for the batch reactor, but with T replaced by tau. Many students get confused by the difference between T and tau. Don't you be one of them. Let's do an example of applying the reactor equations we just derived to the case of the first order reaction of A, minus Ra equals Kca to the first power. In terms of fractional conversion, it's Kca naught times 1 minus F sub A. We'll do the equations in terms of Ca first. For the batch reactor, we have T is equal to the negative integral from Ca naught to Ca of dCA over Kca, which evaluates to T equals 1 over K times the log of Ca naught over Ca. You probably derived this result in high school chemistry, but without knowing what a batch reactor was. The PFR equations are the same, but with tau replacing T. Tau is equal to the negative integral from Ca naught to Ca of dCA over Kca, which evaluates to tau equals 1 over K times the log of Ca naught over Ca. The C* is a difference equation instead of a differential equation. In general, the C* equations are nonlinear algebraic equations instead of differential equations. Tau equals negative Ca naught minus Ca over Kca. Simplifying, tau equals 1 over K times Ca naught over Ca minus 1. In terms of f of A, for the batch, T equals Ca naught times the integral from 0 to Fa of dFA over Kca naught 1 minus Fa, which evaluates to T equals negative 1 over K times the log of 1 minus Fa. Note that since Fa is always between 0 and 1, the log of minus Fa is always negative, making T positive. The PFR equations are the same, but with tau replacing T. Tau equals Ca naught times the integral from 0 to Fa of dFA over Kca naught 1 minus Fa, which evaluates to tau equals negative 1 over K times the log of 1 minus Fa. Again, the C* equations are algebraic. Tau equals Ca naught Fa over Kca naught times 1 minus Fa. The Ca naughts cancel, giving tau equals Fa over K 1 minus Fa. The takeaways from this video are 1. The three ideal homogeneous reactors are batch, C*, and PFR. 2. For constant density or constant volume batch and PFR reactors, the design equations are the same except for the processing time T and the batch being replaced by the space-time tau in the PFR. 3. The C* model results in often nonlinear algebraic equations instead of the ordinary differential equations for the batch and PFR. 4. The design equations can be expressed in terms of fractional conversion or concentration. Thanks for watching. This video was brought to you by the DOFPro team.